everyone, and welcome to Cryptanalysis lecture number 2. We are going to continue our look at algorithms for attacking asymmetric cryptographic schemes today. And while we had a look at the first big group of asymmetric crypto schemes last week with factoring based schemes, today we're going to have a look at the second big group, namely crypto systems based on the discrete logarithm problem. So let's have a look at the plan for today. We're first going to recall briefly what exactly the discrete logarithm problem was, which groups we were having a look at that, or which groups are relevant for cryptography, and then we have time to look at the actual algorithms. And this will be divided into two parts. So first we will have a look at several general purpose discrete logarithm algorithms. This means these are algorithms that work generically in any group. So whether it's elliptic curves or modular arithmetic, they just work because they don't have any special assumptions about the group. And in the second part, we're going to have a look at one example from the family of algorithms which are targeted only for specific groups, namely at the index calculus method. And the thing about these methods is they are only applicable sometimes, but when they're very efficient and beat these ones by far. And since all of this is going to be a bit shorter than the regular lecture, we will still have time at the end to have a look at one of the topics that we skipped last time, namely Lenstra's elliptic curve factoring method. And actually it fits here quite well because it takes up several ideas that we will see earlier in these other parts. And afterwards we're going to return back to discrete logarithms for the summary. So before we go into detail on that, I suggest we have a short recap quiz based on what we heard last week. So now would be a great time to fire up your Menti, either by using the number provided above, which is a bit hard to read, or by just using the link that is right below the YouTube video. So let's have a moment until everybody joins. We will have a total of 4 questions related to last week's contents. As usual, you have limited time. So I think I've set the timer to 20 seconds, but it might feel like less to you because of the lag. So be prepared to have to pick an answer quickly. So let's wait for a few more people to join. I think we should be at least something like 8 to 10 or so who are here and could join. Okay, let's assume the rest is not fully awake yet, so let's head on to the first question. You get a bit more points if you answer fast. So when is the integer factorization problem hard? Is it when n is a particularly large prime, when n has many prime factors, when exactly one of the prime factors is very large, or when it is the product of exactly 2 large primes? Okay, great. All of you got that correct. That's fantastic. So the difficult case is the one that we usually have, for example, in the RSA crypto system, when n is the product of 2 large prime numbers. What about the other answers? When n is just 1 large prime. Now this is a famous quote from Bill Gates, but in that case factoring n is not actually hard because it's just that prime. If it has many factors, then many of these factors are also likely small, making the problem easier because you can first factor out all the small stuff and then you have a smaller number left to work with. And if exactly one of the prime factors is large, it also means the other ones are small, so you can factor them out more efficiently. So indeed, this is the correct answer. Let's have a look at the next one. Oops, skip that one. So, which one is the fastest factoring algorithm? Is it Fermat's algorithm, the general number field sieve, the quadratic sieve we saw last week, or the sieve-rec algorithm we saw last week? Oh, my bad, I forgot to mark the actual correct answer here. That's of course bad for the final tallying of points, but at least it hit a question where there was a lot of disagreement. So let's have a look. The Fermat algorithm is one we had a look at last term in cryptography, and while it was one of the first more efficient ones, it's by far not the fastest. So actually, these are all improvements of Fermat's vectoring algorithm and are a lot faster. Oh, it died in the background. That's great. Then let's have a look. We saw the quadratic sieve last week. This one is reasonably fast. If you remember this L notation, it had the important constant of 1/2 in the beginning. The smaller this constant, the better. So these here essentially can be optimized to have this 1/2 in as the main contributing vector or constant, whereas the number field sieve actually achieves 1/3, which is a lot better. So this builds on top of the quadratic sieve. All of these are sieving algorithms, but this one is the fastest, and this one is the one that all the factoring records are based on. However, it's quite a bit more complicated to understand than the quadratic sieve, which is why we didn't cover it. It involves a lot more math. Okay, next question. Let's hope I marked the correct answer there. Let's see. We also have a cat joining, it appears. So, which of these is an acceptable optimization for RSA? Is it to use a small public exponent, a small private exponent, or a small public modulus? So only one of them is a good idea. Oh, I'm sure I marked the correct answer on that one, so probably Menti is having some issues here. Anyways, it won't have too much of an impact for the final tally because there was again some disagreement, so let's see. Everybody agreed that having a smaller modulus is a bad idea. This is because the smaller the modulus, in general, the faster the factoring. If we look at the private exponent, this would be nice because it would speed up all operations with the private key. However, we saw an attack last week, namely Wiener's attack, which exploited the case when d is relatively small. So when the bit length of d is only 1/4 of the bit length of n or below that, and the two primes are reasonably close together, then we can recover the private key extremely efficiently with this Wiener attack we saw, based on continued fractions. And finally, this one is very popular, and it's actually a reasonably good idea. So if you use a very small public exponent, there are no major problems associated with this. We did see some potential minor problems in the exercises last term. So for example, when when E people use the same small public exponent E, for example, E equals 17 or 65,000 something, then there are actually problems, but these are primarily when all of them encrypt the same message. And since we usually include a sort of randomized padding, these weaknesses can't appear in reality when implemented properly. So this is indeed the best of these ideas. This is not a good idea due to what we saw last week. However, this is maybe not as widely known that it's a bad idea as that case here. It's still important to keep in mind. Okay, one last question to go, of which I'm again sure that I marked the correct answer, but let's see if it shows up. Namely, what is the continued fraction expansion of the number 1/2? Is it 1/2, 0/2, 0/1/2, or 0/5? So here it's important to remember the shape of this expansion. You do have a bit more time for this one. Okay, a lot of love for all of the answers. So let's have a look at what this continued fraction expansion looked like to maybe understand why this one here is the correct answer. So the shape of these expansions was always like the following. It was always something like the first constant, so the first thing in the list here, plus 1 divided by some term that depends on the second constant, so C1, plus again 1 divided by blah 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 and so on. And we get, for a rational number, we just cut off this expansion at some point. So in the case of 1/2, we can write this as 0 plus 1 divided by 2. So this is why 0,2 is the correct answer. This one here would be 3/2 because it's 1 plus 1/2. This one is 0 plus 1 divided by this one here. And the 0,5 here would be 0.2 or 1/5 because the C1 here would be 5. Okay, so that's the correct expansion here. Okay, that's it with the quiz. Let's have a look at the leaderboard, which is now a bit misleading because of the bugs and the correct answers. And of course we have to remove this stuff here. Let's see. I see that a few more people did join in the end, but maybe didn't have a chance to vote. So congratulations to Wolfmeister and the second one, which is, oh, something unparsable. So 3 of you are really close together. Congrats. I have one more question which is not related to the quiz, and that is with respect to the exercises, because as you know, next week is both the handout where we present the actual exercises that you're going to solve, and a few hours later at midnight, it's the team registration deadline. So I'm curious how many of you have already found a partner, even if you maybe haven't signed up yet officially, whether you're still looking for someone, whether you want to do it alone, or whether you're not doing it at all. Okay, that actually looks pretty great. It looks like almost all of you are already set up for this, except one person who unfortunately is not doing the exercises. Okay, then I guess I don't have to say much more about the team finding. I hope the people who wrote something in the Discord chat already found someone. If not, just bump your message again to make clear you haven't. And with this, I think we can go on to the actual lecture. This time, compared to last, I fixed the fact that you can now ask questions at any point and they should pop up here. Okay, let's have a look at the discrete logarithm problem. Okay, so for this we first need to recap a bit some vocabulary that we already know. And the central concept that we are going to meet throughout here is the concept of a cyclic group. So just to remind you, a group was something, it was just a set of elements with an operation that you can use on this set, which has some nice properties. And we call a group cyclic if it has a very special structure, namely if there are one or more special elements, the generator elements, which can produce the entire group. So which means for every other item A in the group, there is some exponent such that I can write this element A as my generator to the power of this exponent. This is equivalent to applying this element to itself t times, where applying to itself here denoted by an asterisk, means the group operation. If the group operation is not a multiplication but a plus, then we write this as t times g. And we call t a scalar because it's just an integer, a number. And this one here is a group element in all cases. So these can both be numbers, like for example in modular arithmetic, but it can also be that this one is a scalar and this has some more complex representation, like an elliptic curve point. I see a question mark here. If there's some specific term or so that I should re-explain, please post in the comments what exactly that is. For now, let's just assume we have these elements, we can apply some operation to them, and we call this the exponentiation. There are two more important concepts here that are related to the security of the scheme, namely the order of elements and groups. The order is simply the term for, in case of a group, how many elements are there in the group, so just the number of elements. For example, the number of points on the elliptic curve. And the order of an individual element is the size of the subgroup that it generates. In other words, it's the number of other elements that can be produced from this element by looking at its powers, so a to the t. And after a certain number of powers, so for example, if I look at a to the 1, a to the 2, a to the 3, and so on, at some point I'm going to hit the neutral element of the group. In case of a multiplicative group, this is usually called 1. And once I hit that, from there on the powers are going to start repeating. So the next one is again going to be a, then a squared, and so on. And this number of different elements that I can produce this way is called the order. So as an example, this is an example you already saw last term. If we look at the elements modulo 11 and look at the multiplicative group, so multiplying these numbers, at least all of those that are invertible, so we're not including the 0 here, then we have the following group. We have a group of 10 elements, all numbers from 1 to 10, which is the prime number minus 1 here. And we see a couple of subgroups here. So for example, if I look at powers of 1, no matter how often I multiply 1 to itself, I always get a 1 back out. So the order of this thing is 1. If I look at 10, I can produce two numbers, 1 and 10, because 10 is the same as minus 1, and minus 1 times minus 1 equals 1. So it has an order of 2. And similarly, I have an order of 5 for some of the other elements and an order of 10 for a couple other elements, and these are the generators, because they can produce all the 10 numbers here. And you can see that 2 is a generator right in this picture here, because here I'm listing the powers of 2. As long as they're below the modulus, they just stay the same. If they get above, like for example, 2 to the power of 4 equals 16, I reduce it by 11, I get 5. And again, I double and reduce if necessary, until I get back to 1. So this is an example of a cyclic group, and these are the corresponding generators. And if we're looking at discrete logarithms later, we're always going to be interested in finding how often do I have to add an element to itself to generate some other elements. So it's very important how many elements I can generate from some basis number. And now there are some important questions related to this. So I would be interested in how many strong elements are there. So these would be the strong elements because they can generate everything else. And how frequently do I run into weak elements? And how can I characterize those? So let's have a look at this question here and at some observations that are related to the group order. So we already said that the element also has an order, which is how many numbers it can generate. And we noticed on the previous example that all of the orders that I get here are divisors of the full group order. So the full group order is 10 equals 2 times 5, and each of these is a divisor of that number. And that's more generally the case. And I actually can reason about this if I know that I can predict the order of some power of an element, if I know the order of the individual element and the group order. So if I have some element here, a, and I want to know the order of a to some power of k, then this is at most the same order as a, but if the exponent has a common divisor with the order, then I divide it by that. So maybe if we look at an example here, so for example, if I take 2 to the power of 2, which is 4, then the exponent here, the 2, has a common divisor with the group order, which is why the order of 4 is no longer the full 10, but it's 10 divided by 2, so by the greatest common divisor, which is 5. And from this I can derive another very important thing. Now please don't remember the details of this, but remember the main message. Namely, each group has a very specific number of elements of a particular order. If I'm interested in an order D, and this D divides the group order, then I can say that there are exactly phi of D elements of this order, where phi is the Euler phi function that we met already, which is approximately the order of magnitude of D itself if D doesn't have too many prime factors. And in particular, I can actually provide a bound, a lower bound on how large this phi function is. So you can see here it's of the order of D divided by log D, and this is a really tiny thing, so it doesn't have a lot of influence here. So essentially, if D is large, then there are many elements of this large order. And this is really good news for us. It means that more elements have a high order, if high orders exist in my group. So if I have a very large divisor of my group size, then I will also have many elements that, or relatively many elements that have this order. And this is good because they are good basis points if I am interested in the discrete logarithm problem, our main topic here. So let's recall what this was like. I've listed here the general discrete log problem, which works for any group, this definition. So what I need is some cyclic group, finite cyclic group, so meaning there are not infinitely many elements in it. And I have some group order n. If I now have some generator of this group and any other group element, then what I'm interested in is to find the discrete logarithm of this challenge element. So in other words, I'm looking for an exponent, for an integer x, such that when I apply the group element, the generator, x times to itself, I get the target element that I'm looking for. This is the main problem. And the purpose of this lecture is now to discuss how hard is this problem and what can I do to solve it. And so first I want to discuss two aspects that are related to in what way the hardness of this problem depends on the group and the generator that I choose, whether this has any influence. So let's first have a look at whether it makes a difference which generator I choose if I have multiple generators which all have the same order. So assume I have two generators, let's call them alpha and gamma, and I'm now trying to solve two discrete logarithm problems, or one of the two. One of them is to the base alpha and one of them is to the base gamma with the same target element. The question is one of the two fundamentally easier than the other ones? Is there some property of the generator that I can exploit for this? And as it turns out, no, it doesn't really make a difference. And I can see why that is as follows. So the first observation here is, I assumed I have two generators. So each of them generates the entire group, so they can also generate each other. So for example, I can write one of them as the other one to the power of some exponent. I don't necessarily know easily how to find that, but I can write it like that. And now let's have a look at this problem here again. I can now rewrite the equations I have, so the first equation here, and then I fill in the other equation that I have here, replacing the gamma by alpha to the w, because that's the exponent that generates gamma. So I have now this equality here. This is an implication of these two here. And if this is to be the case, then the exponents here are equivalent modulo the group order of the group I'm working in. Since I said I'm working in the group of multiplication modulo some prime p, this group order is p minus 1. We will actually see this quite often, switching between computations in the exponent, and computations in the group. This will be part of several algorithms later. So now let's say these two are the same. And what I'm interested in is finding one of the two from the other. So x is the logarithm I'm looking for here, and z is the algorithm I'm looking for here. Now let's assume I have an algorithm for computing one of the two logarithms. So let's say, for example, that this one here is a lot easier than this one here. So logarithm to base alpha is a lot easier than logarithm to base gamma. Now if I look at this equation here, I can actually write each of these integers here as a logarithm to one of the bases. So x is the logarithm of y to basis alpha. That's what I see from here. W is the logarithm of gamma to the base alpha. That's what I see here. And the last number z here is the logarithm of y to base gamma. So in other words, I now have an equation that links some logarithms in alpha and some logarithms in gamma. And I can simply rearrange that. So I can, for example, divide by this number here. Then I have a left-hand side with alphas and the right-hand side with gammas. And if I now can, for example, efficiently compute everything to base alpha, then I can just easily compute this and easily compute this. And as a result, I obtain efficiently my logarithm to base gamma. So in other words, if this one here were very easy to solve, then this would be also very easy to solve, because I simply need to evaluate two logarithms of that sort to get one logarithm of that sort. So in other words, the choice of the basis can't be that important, at least in the field in the group we're looking at here. Okay, so this is with respect to the difficulty of the problem based on the generator. There is no real impact of the choice of generator. So let's have a look at another ingredient we had, namely the choice of the group. And here it turns out that this actually has a huge impact on the difficulty of the problem. And this is despite the fact that all groups of a certain size are in a sense fundamentally the same. They have an isomorphic group structure, meaning they have the same sort of subgroups, they have elements of the same orders and so on. So the structure, if you draw a picture of the group, is actually the same for any two groups of the same size. However, being able to solve the discrete logarithm in one of the groups does not translate to being able to solve the discrete log problem in all of the other groups. Now this sounded a bit abstract, and I see we have a comment here, so let's have a look at that. Assuming I can log in here again. So the question is, sorry, it's a bit hard to read. So if I solve the DLP for one generator in a certain group, the whole group is broken. Yes, in the sense that if you have an algorithm that generally solves the DLP for one generator, then the whole group is broken. Because all of its generators are equally weak. If you solve just one individual discrete log problem, like for one challenge value, and you don't have a general efficient method for the other ones, then you can't necessarily break anything. Because as we saw on the previous slide, you can do it if you can solve two specific DLP challenges. So if you had just one random lucky success, that's not a problem. But if you have a general algorithm for one generator, then yes, you have a problem and the group is broken. Okay. So let's now get back to the groups case. And I have an example here where you can see that in some groups, the discrete log problem is actually very, very easy. And this example is also in modular arithmetic, but if we look at the additive instead of the multiplicative group. And it turns out that here the discrete log problem is actually completely trivial, and it also doesn't really deserve the name log problem. So how does this problem look like in this group? I'm again interested in how often I have to apply the group operation to some generator, like for example the number 1, to generate a particular challenge value in the group, so modulo n. Now this I can simply write as I'm looking for some value x such that g times x equals y. Now this is an extremely simple equation because I can simply divide by g. So bring g to the other side and voila, I have a very efficient method to compute x from g and y because I simply multiply y and the inverse of g to get x. So in other words, the discrete log problem in the additive group here is simply the division problem, which is not a problem at all. So even though the other groups are isomorphic to this group here, we can't move, or we don't know how to generalize this very easy algorithm to other operations, to other representations of the same group. So what we need is some clever groups where we do not know such a simple algorithm. And this is essential whenever we want to use this problem in a cryptographic context, whether it's the Diffie-Hellman key exchange scheme or the DSA digital signature algorithm or its elliptic curve variants and so on. In all cases, we need a good group here. And the two primary groups that we use are the two, so one we already saw, namely the multiplicative group modulo prime number p. Typically this is done for where the p has an extra property, namely it's a safe prime. This means that the number can be written as p equals 2 times some other prime value plus 1. And this is because then the group order, which is 2q, has one very large factor, which makes most of the discrete log algorithms harder. So that's what a safe prime is. And the other kind of group we're interested in is the elliptic curve group. So I want to briefly recall what this group looks like because we're going to see it again at the end of the lecture, and also to have a more general picture of groups in all of the following. So as a reminder, in an elliptic curve group, we represent all our group elements as two coordinate values, x and y. And we pick exactly those combinations of x and y where the two variables together satisfy some equation which defines the curve, namely an equation in Weierstrass form. And if I choose x and y, for example, to be real numbers, this might look something like the following. And to make it a group, I also need an operation and a neutral element. The neutral element is an element not actually on the curve, but a special point, which we could informally call 0 infinity. So it's infinitely up on this axis here. And we have a group operation, which we can define in a graphical sense, but we will also revisit the mathematical formulas for that later on. So the intuitive version is to add 2 points on the curve. I draw the chord through these two. So I draw a line through these two, computing the slope here and the basis point. I intersect it with the group, with the curve in one more point, and then mirror it along the x-axis. And that's the result of the computation. Never mind the details, and in practice it doesn't actually look as pretty as this one here, but what we do get is a group with a two-dimensional representation, which we can use. To make it usable, we don't actually use this continuous version, so over the real numbers, but we look at the discrete version, so where my coordinates are also elements modulo some prime number, or more generally in some finite field. So I have two important types of groups we're going to talk about. The modular group, some people also call it the finite field group, which is a bit confusing, I think, which is computing modulo a prime number and taking the multiplicative group, which has order prime number minus 1, or this two-dimensional case where the exact order is a bit different and cannot always be predicted just from knowing the underlying operation. So in this example here, this is a curve over Z17, so computing modulo 17. And it turns out to have an order of 18. So exactly 18 points here, including the neutral element. Okay, and the question how many points are on here is actually quite important. And this is because we already saw this is one of the main security parameters. We want to know how many elements can be generated from something, because the higher, the more difficult the discrete log problem is going to be. And we do have an approximate statement on the size, which is the Hasse theorem. And it tells us that the number of points on the curve is approximately equal to the size of the finite field, but plus minus some error term, which also depends on the size of the field. So it's somewhere in the vicinity, but it varies, and it depends on which equation exactly I choose. But the main message is, if I know the size of the underlying field, I also have a rough approximation of the group size here. And I want to have some base point for my discrete log problem, so some generator of a reasonably large subgroup. So the number of elements it can generate should also be similar to the size of the group. This is why the size of the underlying field is essentially the main security parameter of this group. Similar to this case here, where the size of the field is a very precise security parameter of this group. Okay, so let's go and solve this problem, solve this discrete log problem, with some general methods that work in any group, whether it's elliptic curve or something else entirely. And I guess you can all think of a very simple algorithm how to solve this. Does somebody have any suggestions? So how would you, if you didn't know anything else and had to solve a discrete log problem, what would you do? Any ideas? Having question marks, okay. Let's wait a few more seconds if somebody decides to come up with some very straightforward solution. I do see that there is a suggestion. So let's see. Oh, we actually have several suggestions. Yes, just try every number, where every number means every possible exponent. And that's actually exactly the same as the other suggestions that we have here, namely brute force. So thanks for these suggestions. These are exactly the first algorithm that I want to have a look at, just so that we have a base point to start from. So I called it here exhaustive search, but it means exactly what the three of you wrote. Namely, I simply try every possible exponent and see if it matches the challenge element. So I first take g, multiply by g to get g squared, see if it matches, multiply by g again, see if it matches, and so on. Very straightforward. Question is, how long does it take me? Well, that depends, of course, on the order of g, because this order gives me the maximum number of tries that I can take. Once I've gone through this order of g, I've exhausted all possible options. Assuming that g is a generator and n is the group order, so n is the same as the order of g, then I take at most n operations. On average, n half. So I've written here O of n because on the following we also have just O notation, but actually it's more precise than just that. Now, this actually looks very nice and linear. Why do we call it exponential? Well, we call it exponential because the size of the group is actually exponential in the number of bits I need to represent elements from the group. So in other words, it's exponential in the size of the challenge. For example, if I have a group of, if I take the multiplicative group with a 128-bit modulus, then each element takes 128 bits to store, but the size of the group is something in the area of 2 to the 128, so exponential. Which means this innocent O of n is actually a very bad and very exponential runtime. So for example, if I had a 256-bit modulus, it would take 2 to the 256 tries. Let's try to do it better. So let's have a look at first an optimization that will be a sort of preparation step for the next one. And that is to build an index table. So this is a sort of time memory trade-off. What I can do is I can pre-compute some data so that at a later point I don't have to do the computations again, I just have to do a sort of table lookups. So what I can do, if I know that I very, very often have to solve discrete log problems in some group, I could prepare a list of all powers of my generator and sort it so that I can index it very quickly. So what I've done here is computing modulo 11. I've taken all possible exponents from 0 to 9. I could also go from 1 to 10, that would be the same. And computed 2 to the power of this exponent, reduced it modulo 11, and then sorted by this value here. So here we can also see very nicely that this number is actually a generator because it generates all other points on the group. And if I have this table, then every new discrete log that I have to compute is just a table lookup of O of 1, approximately, depending on how exactly I implement it. But in cryptographer terms, it's O of 1. So that's a nice speed up that doesn't really reduce the overall cost. Actually, it increases the overall cost because storing O of n things is even worse than computing O of n things. But I do have an efficient version if I have to do this very often. It's also a nice starting point for the first more efficient general purpose algorithm that I want to have a look at. And that is the so-called baby step, giant step method. And this is a more balanced trade-off. Again, we're trying to do the same thing, finding our x. And the clever idea of this baby step, giant step method is now I don't look for x as a whole, but I divide x into two parts, like the most significant and the least significant bits. And then I try to find these separate and try to find a matching combination. So what I do is, if I take the upper and lower most significant bits, then this is essentially cut at square root of the total size as a value. So I take this value m here, which is square root of the total size of the exponent. So that's a separator here. And I will rewrite my exponent in some more significant bits I and some less significant steps bits j. We also call these the giant steps because increasing it by 1 increases this bit here by 1 and thus makes a very big step, whereas these are the baby steps, just increasing 1 just steps forward by 1. And I can now fill in this decomposition into the original equation. So my challenge value equals g to the x, which I can divide into g to the I times m times g to the j. Having g and j is really a bad choice here if you want to pronounce it, I notice. Okay, what can we do if we have this? We can bring this part here to the other side. And then we have a nice equality where one side depends on j only and the other side depends on I and the challenge only. And what I want to do is I want to separately have many candidates for this and many candidates for this in order to find a collision which gives a nice combination and a candidate value x. So what I do is I pre-compute many of these baby steps here, store them in the table, and then I compute many of the giant steps here and look whether I find a match in the table. If I have a match, then I have a combination such that this equation here works out. So I have recovered a valid logarithm x. That's great because now I've suddenly reduced this by a square root factor. So the number of values the number of all possible values for j is just approximately square root of n, and the number of all possible values I is also just approximately square root of n. Or in other words, half the bit size of the original. And now what I do is I have again some storage and some time lookups, and I can actually make more clever trade-offs here. So what I can do is if I say that table size is more costly than time, then I can make the table a bit bigger, a bit smaller, sorry, so compute fewer baby steps, and in contrast make more lookups, so more giant steps. So this way I have a really flexible trade-off that I can optimize depending on the ratio of storage cost and computation cost. So let's have a look at an example. For some tiny numbers, namely I'm trying to find the logarithm base 2 of 22 modulo 37. So the group size is 36, meaning I divide at square root of 36, which is 6. So I write my exponent as some multiple of 6 plus j. And now I compute values for both of those. Here are some baby steps. So for each j, I just take 2 to the power of j, very easy. And then for each I also take g to the power of minus mi times my challenge value, so the formula from earlier. I've sorted it here, that's why the order is a bit confusing, so that it's easier to find matches. But in reality, I don't actually have to store them, I can actually just compute each one and look it up here. In any case, we see there is exactly one collision here. I hope all of this colliding stuff reminds you of some of the parts in cryptography. We have exactly one collision in this combination, which is I equals 5 and j equals 1, gives me a valid combination for x. So x is simply 5 square root of n, I 5 and j 1, which if I evaluate it equals 31. And this is all a lot faster than if I would just have tried all 31 possible exponentiations of 2 to find the right result. So that's great. And it actually also gives rise to another optimization idea. Now, we already said that we actually don't need 2 tables, it's sufficient to store just one, but maybe I can optimize this to even do it without storing stuff. Do you have any ideas how I could accomplish this? Or which method that we saw in the context of hash functions do you think could be a good idea here? Any suggestions? So somebody has a suggestion. It's called row collision search, and that's exactly what I was looking for. So memoryless collision finding is another term for it. Thanks for the suggestion. And we actually already have a method how to do this suggested here, namely the tortoise and hare algorithm. So thanks a lot for the answers. And let's switch back to the slides and have a look at how this works. So if you remember, in cryptography, we had the case that we also tried to find collisions between tables of hash values because we were looking for hash collisions. And here we also have the case that we want to have a collision between 2 tables. And in cryptography, we saw that one trick how we can do this in the same asymptotic time cost, but without any asymptotic space cost. I don't know why it says square root here. I think I should remove that. We can do this by specifying a particular update function that updates one potential value that could collide to another potential value. And then we loop through all of these values using, for example, the tortoise and hare algorithm until we find a collision. And this collision must exist at some point, because if I have only finitely many possible values, for example, exponents in my discrete log problem or hash values in case of the hash function, then I can't have infinitely many different ones. At some point, I need to run into circles. And then using, for example, the tortoise and hare, which uses 2 runners of different speed, I'm not going to recall the details here, I can actually find this entry point here. So the question here is, how can I set up this search graph for the case of the discrete log problem? how could I choose this update function here? And of course, I also need to find out how such a collision here would be possible to translate back to a actual discrete log problem, discrete logarithm. So there are questions like, how do I get the challenge in here, and so on. So let's have a look at that. And the main idea is the following. It's a bit inspired by the baby step, giant step algorithm we saw before. We also write our intermediate values as some combinations of powers of y and powers of g. If I go backwards a bit, we also had this here. So here we had a simple power of y, which was just y of the 1, and a power of g, which was g to the minus m times I. And we are going to do, we also had this here, by the way, which was y to the 0 times g to the j. And we tried to do the same thing, but with many different exponents for y and j. And we're now going to have to try and find two different intermediate results here, which produce the same value. So we're looking for a pair of exponents ab and another pair ab, such that y to a g to the power of b with the one pair equals the result when I use the other pair. And the exact values of a and b should be different from here. Why is that useful? Assume we have found one such combination. So assume we have found such a collision in the graph I showed earlier. What do we get? We're going to do the trick that we saw before. We're going to look just at the exponents and not at the group elements. So what are the exponents here? The exponent here is x times a, because y is g to the power of x. So x times a. And we also have x times a here. So I bring this to the other side. So on the left-hand side, I have x times the first a minus the other a. And here, the exponent I have is b. Here it's again b. I bring this to the other side. So I have the one b minus the other b here. And again, the whole thing is modulo the group size, because I can always do all my operations modulo the group size here when I'm in the exponent. So if I have found such a collision and I know the a's and b's, then I know this equation here, and voila, I have now magically transported my discrete log problem into a problem that looks very much like the easy one we saw before, which is the division problem. I can now simply divide by this value here, and voila, I get x. This only works, of course, if the two a's are different. This is why I'm looking for a collision with different values here. Okay, so now I guess we see why we want to find such a collision. Now the question is, how can I make this update function here, this runner function, which updates one such y to the power something, g to the power something to the next one. Now there are several possible choices, and one of the choices that is most widely used or proposed is the following. So I make a random looking choice because if I have just a very simple update rule, like I always just increase the counter of y by 1, this is not going to be like a random walk. This is going to be an exhaustive search essentially. So I need to randomize the exponents a bit, which means I do different things depending on what value I currently have. And in some cases, I increase only the first exponent, in some I increase only the last exponent, and in some cases I double both exponents. This is just one possible way of more or less randomly walking through a big set of exponents without looking like regular exhaustive search. And if we look at the group elements, this corresponds to either multiplying the previous result by y, or multiplying it by g, or squaring it. You can also translate this to elliptic curve terms, I guess. So either add the base point or add the challenge point or do a doubling. There are many other possible choices for this function. I just need something that walks around randomly. Now, if I use this update function, I can use one of the cycle finding algorithms that I know. This could be the Floyd, tortoise and hare algorithm that we already saw, or something more efficient, because almost all other versions are a bit more efficient than Floyd's. So you could, for example, use Brandt's algorithm or Nivash's algorithm or what have you. You can also do trade-offs where you have more than just two runners, so where you have a larger set of distinguished points, there are many possible options. But in the end, you have this update function and you're looking for a collision. And you can do this for any group you like. And by analyzing the average length of the cycle here, you can also get that this average runtime still holds. For the same reason, or for a similar reason as in hash functions. So to summarize these general purpose methods, we saw that two of them have this same complexity of square root of n. So this is exponential, but the exponent is only half of the size of the security parameter. So in other words, as a very minimum security level, if I want to achieve n-bit security, I need to have groups with a size of at least 2 to the 2n. So the doubling is because there's a square root here and not just n. And the 2 to the something is because the group order is the exponential thing. So for example, if I'm looking for 128-bit security, my groups should have a size of at least approximately 256 6-bit representations, or 2 to the 256 elements. This is a lower bar, and this holds for all discrete log methods. So that's why whenever you look at elliptic curves, you have at least this equation here. However, what we can now see, or what we will see in a moment, is that for some special groups, I can have more efficient algorithms. And if that's the case, I need to choose larger security parameters. And two of the most well-known algorithms are first the Polik-Hellman algorithm, which I'm not going to cover here because it takes a while and it's only very rarely applicable. And the second one, which we will have a look at, is the index calculus method, which is a lot more efficient. And its efficiency is actually very closely related to the efficiency we saw for factoring. And it will also show us a bit how discrete log and factoring are actually not so different from each other and can be treated with some of the same methods. And actually, the factoring records that we know were also done with an advanced version of this index calculus thing, which is again very closely related to the same thing for factoring. So both for discrete log and for factoring, the best methods are based on the general number field sieve. And again, we're not going to look at that because it's messy and complicated. We're going to have a look at the closely related index calculus. And this works as follows. It's also based on a sort of sieving, and it involves some logarithm. But let's have a look at it step by step. The first step looks very similar to factoring because I'm choosing a factor base consisting of a couple of prime numbers. Then I'm again going to do the same thing as in sieving algorithms and going to collect relations. However, these relations are going to be different from last time. Last time we had a look at squaring relations. Here we're going to collect discrete log relation. And then finally we're going to have a linear algebra step where we solve a linear equation system. In the factoring case, this was for finding a suitable combination of squares. Here it's going to be to determine the discrete logarithm of the primes in the factor base. So in other words, all of this up to here is actually just, up to here is a pre-computation step where I just prepare data for my factor base. And then when I have an actual query, I'm going to have a look at this last step again. I'm again going to collect some relations and try to find a suitable combination that allows me to find the discrete logarithm of my challenge number based on the discrete logarithm of the prime numbers. And usually that's a bit of a difference compared to factoring. Usually the pre-computation part is a bit heavier here and the actual queries are cheaper. Because in the pre-computation step I already handle everything about this large database. and afterwards the stuff is faster. The runtime I get out of it is very similar to what we saw last week. It also has this L notation, which denoted this thing halfway between polynomial and exponential. And it also has the factor of 1/2 that we saw there. So let's have a look at all of these steps in some detail to actually see why this makes sense. So the first step I'm not going to cover again because this is very easy. I just choose many small prime numbers. That's it. Of course, there is some challenge in how many I choose, and like for factoring, there are some general recommendations, like some asymptotic sizes that this should have. But for now, let's just assume we have chosen some limit and we take all prime numbers up to that limit. Now what we want to find is, in step 2, we want to find the discrete logarithm of these prime numbers. And this is going to work as follows. So I'm again doing something like we did in random squares. I'm looking at random variations of what I'm looking for. So what I'm looking at is I will take my base element, my generator, and raise it to random powers, and then try to see if I can factor the resulting number. So I take g to the t, and I can see if I can write this as a prime factorization using only the prime numbers in my factor base. So this is cheaper than general purpose factoring because I only want to test it with these small prime numbers where it's supposedly cheaper. So that's the first step. And then I'm going to do the same thing we already saw a couple times. I'm going to look only at the exponents. So what exponents do we have here? On the left-hand side, clearly the exponent is t. How about the exponents here? So apparently I have an exponent a here. However, the question is, what is the exponent with relation to g and not p? So what I need is I need to rewrite p as g to the power of something, and that then to the power of a. And this something, in other words, is the logarithm of p. So this thing here is the same as g to the power of log p times a. So log p times a goes here, and that's the logarithm of the thing. And I do the same thing for all the other terms here. So I always get the original exponent I found by factoring times this unknown logarithm of the prime number. So far I can't actually compute these numbers, I can just write it down formally. I know t, I know all the a's, and these logarithms are unknown variables at the moment. These are what I'm trying to find. The good news is that I can do this relatively easily because I can solve very many of these relations. So in other words, I try many t's, try to factor all of them, and each one that factors successfully gives me one of these equations. Now, if I have b unknowns in this here, one for each prime number, and I successfully collect a total of b relations, I actually have a linear equation system. T equals a times something plus a times something plus another a times something. And I can solve that, even if the equation is not over the real numbers, but modulo p minus 1. That doesn't really change anything. So I collect relations and I solve the corresponding equation system. As soon as I have enough linearly independent equations, I can do that. And solving an equation system is, asymptotically speaking, cheap. However, when I have a really large factor base, it actually turns out that this can be the dominating step of the whole thing. Because the size of the equation system is quadratic in the size of my factor base, even though it's relatively sparse. And solving an equation system has an even higher exponent than just 2. So it's 2 point something. So this is actually pretty expensive also because you have these huge amounts of data that you need to work with. So implementing it is hard, but asymptotically speaking, it's easy. Okay, what have we found after this step 2? If we solved it, we now know the logarithm to base g of each of these prime numbers. What we haven't talked about yet is the challenge number y. And now we need to use this information here to find out something about our challenge number. So let's do that. And this is the step number 3. So we now have our challenge number and we want to find the exponent. This is again going to be a randomized step where I try to collect several equations. And I do this by choosing some random values s and computing the result of y times g to the power of s. You will remember that this is the sort of equation that we already saw several times now in the baby step giant step algorithm and in the Pollard row algorithm. And this is again so that we have some random looking thing of which we know part of the exponent. So we can now rewrite this if we take the original equation here. First we need to do the same thing as in the previous step. We need to take this and try to factor it. That's why we try to have many random candidates. So we can try to factor each of them with respect to the vector base. Assume we have found some value s such that we were successful. So we took this value modulo p, factored it successfully, and now we know the exponent for each of our prime basis vectors. Now, this is the step that I wanted to talk about before, namely the step where we again look at all the exponents in this equation. Which exponents do we have? This one here can be written as g to the power of x. That's our input. I've written here log of y, but this is just the unknown x that we are looking for. The exponent of this is apparently s. The exponent of this here now is again this exponent times something, but by now we know this something. We do know what the logarithm of our prime numbers is, so we can fill this in from the pre-computation step. Same thing for all the other prime numbers. I again always have the exponent I found here by factoring times the logarithm, which I know by now. So in summary, I know all of this. I do know s because I chose it randomly. And once I have found all of this, it will be trivial to find out that value because it's simply all of this minus s. So let's have a look at an example. Namely, let's again try to factor something around the number 37, but this time with a larger modulus. Because this algorithm is faster, we can deal with larger moduli. And let's have a sweet and tiny vector base of 2, 3, 5, and 7. So if you remember, what was the first step? The first step was that we try random exponents t and try to factor the result. So I've chosen some completely random numbers here and compute my basis g to the power of these random numbers. I reduce them modulo p and try to factor them. And these numbers are not actually random. Those are the ones I could successfully factor out of the ones I tried. So what do we have here? 2 to the power of 1 is the first lovely start. And I can also factor the other ones using only prime factors from my vector base. So let's translate this to the exponent step. So I take the logarithm on both sides. For example, in the last line, 37 equals 1 times log 3 plus 2 times log 5. This is now an equation modulo the group size, so p minus 1. Okay, so I have collected a number of lovely equations, and what I'm looking for is these unknowns here, log 2 of 2, 3, 5, and 7. Since I have 4 unknowns here and 5 equations, this should be plenty, so I should be able to solve this. Let's have a look. Indeed, this works. If I just apply something like Gaussian elimination or so to this step here, this is what I get. I can already read the first one off right here, very easy. So log 2 of 2 is apparently just 1. What a surprise. The next one also directly gives me log 5 by simply bringing 3 to the other side here. So log 5 equals 8 divided by 3, which is 46. If I know 5, I can plug it in here get log 7. Log 3 I also can directly read off here. It's apparently 7. And finally, I actually know all these ingredients here, so I could have saved myself the effort of doing this last thing here. I don't actually need it. Okay, so great. We have now found the logarithms of all our prime numbers in the vector base. Now it's time to look at our challenge value for the first time. So we will now take over this bit of information here and try to combine it to find something out about 37. Okay, so to do this, we try to find random exponents s until we can factor something. So I can just try not random values but small values because it's easier to compute. I can try first y times g to the power of 2, then to the power of 3, and so on. I've written here the factorization. Usually if you implement this, you wouldn't actually get the factorization and then notice it doesn't fit in the vector base. You would just try only the prime factors of the vector base and would notice that there is some remainder left at the end that you can't factor. Okay, so if I do this, I have to do a total of 5 steps until for s equals 6, I'm actually successful, because our challenge value 37 times g to the power of our counter 6 here, when reduced modulo the prime number, actually gives us 10, which factors nicely over our vector base, 2 times 5. What do we do now? We again rewrite our lovely equation in terms of exponents only. So on the left-hand side, we have the logarithm of 37, our big unknown that we want to find, plus 6, which is written here on the other side, minus 6, plus now everything I need to build these ones here. So it's 1 times the logarithm of 2 plus 1 times the logarithm of 5. And if I sum all of them up, I get my result of 41. Okay, so this is our final discrete logarithm, the logarithm of 37. Okay, now in this case it's not so obvious anymore that all of this is actually less effort than just trying the 41 times, but if you're a computer and not a human, and if you look at asymptotics, this algorithm is actually a lot faster than all of the previous ones. So let's summarize here these special methods. I mentioned this Pauli-Kelman algorithm, but didn't cover it. What it does is essentially it tries to reduce the discrete logarithm problem modulo some big N into logarithm problems modulo the prime factors of N. So its complexity also reduces to the complexity of the prime, but it's still square root of this number. So essentially the runtime is dominated by this part here and is very similar to the square root algorithms we saw before, except if my group order has only small prime factors, because then this one here is faster. What we did have a look at was this one here, the most efficient of the ones we saw, but not the most efficient overall. So an improvement on top of it is this general number field sieve, which is better but more complicated. And when did this work, or what was the main idea that we used here to make it work? What we did is we used the fact that all of our numbers, all of our group elements, could be factorized. So we used the fact that we have this sort of prime elements which can together generate all of the other elements. Not in terms of the group exponentiation, but in terms of prime factorization. And this means we can only use it whenever there's a concept similar to this. So whenever we have something like prime factorization within the elements of our group. And this is something we do not have in elliptic curves. At least unless the elliptic curves are somewhat special and super singular and whatnot. Or over fields of a small characteristic in certain cases. Anyway, we don't usually have that in the curves that we use, so we cannot apply this algorithm in case of the elliptic curves we use, which means we are reduced to using only the generic methods, which means in case of elliptic curves, we're left with this square root of n complexity, so exponential, whereas if we're dealing in the multiplicative group modulo something, we suddenly have this algorithm with sub-exponential runtime, meaning the key sizes for finite field arithmetic are going to have to be a lot bigger. More specifically, the key sizes we need are essentially the same as we need for factoring, because the algorithms we have are also very similar. And this is why, for example, in elliptic curves for 128-bit security, you get something like 256-bit keys, whereas if you do Diffie-Hellman, for example, over the multiplicative group, you get key sizes of around 3000 bits. The approximate growth of these is, if I remember correctly, something like a cubic function, whereas in the case of linear curves, it's a linear growth in the security parameter. Okay, besides these specialized methods, there are other specialized methods that I'm not talking about today, but I think today hopefully convinced you that factoring and discrete log are not that different. And if I can do the one thing, it's often a useful ingredient for doing the other. And in fact, this also holds for quantum algorithms. So Shor's algorithm, which is actually a factoring algorithm, can also be adapted to find discrete logs. So let's have a look at some records to get a feeling about what's possible with academic computation times. Up until recently, I always had to list these old records about 768-bit moduli, both for factoring and for discrete log, even though the discrete log record for this size was a lot younger than the other one, which has also caused some people to think that the discrete log problem might be a tiny bit more difficult because it took longer and more core years in order to achieve similar results. At least for the pre-computation part, the actual challenges are a lot faster. So the people who have done these pre-computations here can now solve every new challenge in this group much faster. However, as we already saw last week, there are some new records from only approximately 1 year and a few months ago, which were about 795-bit records. These were done at the same time for factoring and discrete log of the same parameter sizes in the same publication. And actually the discrete logarithm was only a tiny bit slower, a couple thousand core years slower than the factoring. And the factoring one has actually been improved by now by the same team with the same methods, because they were very lucky and this number was breakable faster. You might be wondering why this strange step size here. It's not like they tried all the numbers in between those, but all of these records are based on public challenges. So RSA Security, as a company who already wrote out these challenges ages ago, so in the previous millennium, and they only had challenges in certain step sizes, and these step sizes were actually not in bits as we would do it probably now, but in decimal representation. So they had something like a 240 digit challenge and a 250 digit challenge and so on in decimal digits, which leads to somewhat awkward bit sizes. So this is a relatively natural bit size, I guess most of you would say. These ones are not. That's because they are based on specific integer digit sizes. And both of these were done with the same records, the same methods. I also want to mention a much smaller record, but at least as important, namely on the elliptic curve equivalent of this problem. So the elliptic curve discrete log method, where we saw the sieving stuff doesn't work, we need some generic method. So the Pollard row algorithm, which we saw today. And with this method, Bernstein et al. Were able to find the discrete log of a 118-bit binary curve. There are a couple of related records that are also important because they are on slightly different structured curves, like on a prime curve and so on. So you might find a couple of records where all of them are the currently best ones in their category. If we want to compute the runtime that we saw here, the core years, into the metric we usually use to evaluate the cost of an algorithm, which is in this case arithmetic operations, and in this case crypto operations, then we would get approximately the following. So these 250 FPGA years are very, very roughly 2 to the 60 crypto operations, whereas these records here correspond to very roughly, so at least the older ones do, I didn't recompute it for these here, very roughly 2 to the 76 simple operations. Why the big gap here? That's because these here are measured in a simpler unit, which is cheaper per execution unit, just one arithmetic operation, whereas here one execution is an entire computation, so for example an addition on the elliptic curve, which is more expensive. So fewer of them are possible with a similar cost. Okay, so much about the records, and now let's jump to the short detour I promised earlier, because we're already talking about elliptic curves, about one other use of elliptic curves, namely for factoring. This is just a couple of slides. If you downloaded the slides from the website, you will see that this part here is missing because I already had it in the previous slide set. Okay, so how can we use elliptic curves to do some other interesting stuff, namely to break stuff? This idea is based on one other factoring method that some of you already know from cryptography, namely Pollard's P-1 method. I don't want to go into the details, but the basic idea that this was based on is if I have a group and I know its group size, then Fermat's theorem tells us that a to the power of the group size equals 1. We saw this in a slightly different phrasing in the RSA lecture. There we had written something like a to the power of phi of n, where n is the modulus. So this holds, and in summary what this algorithm here does is it wants to factor a number n into 2 primes, and it does so by sort of pretending that n would be a prime number, happily doing computations under this assumption. So in particular, if n would be a prime number, then multiplying modulo n would form a group, and I would have this property here that a to the power of n minus 1 equals 1. And if a is a generator, then actually no other exponent, no smaller exponent does this. However, since n is actually not a prime and we're just pretending it is, we will notice some deviations from this behavior. This is because the actual underlying groups are, if I do the same computations, modulo p and modulo q instead. And if I do computations modulo n, and I would look at the results modulo p and q in the background, then I would at a sooner point hit this neutral element here, and I would be able to detect this. This sounded a bit complicated, but what I effectively do is I take some big numbers k. I hope that k is actually a multiple of the group size of one of the smaller groups, modulo p, and I happily keep computing some elements a to this large to the power of this large exponent here, until I run into a number, so until I essentially hit, if k is large enough, I hit the group order, and then the result here is 1 modulo p. Now I don't directly see this because I can't compute modulo p, I can only compute modulo n, but when this happens here, I can still detect it, because then a to the power of k minus 1 would be divisible by p, if this equation holds modulo p. So a test, so that I can test if in the background, in the computations modulo p, this happened, the test that I can do is I can compute the greatest common divisor of this thing here with n. And if this happened in the background, then both things here are divisible by p, and the GCD of the two, the greatest common divisor, is also p. And the problem about this algorithm in the original way is the following. It only works in some cases. It only works if this group here has an order which has only small prime factors, because then I can with reasonably efficiency find a k that achieves this here. So it only works efficiently if the group order of modulo the unknown prime p is smooth, has only small prime factors. And the big trick that we can use here is that this is actually, as we saw today, not the only way how we can generate a group by doing some computations modulo n or p or q. We do know another group, and that is the elliptic curve group. And the lovely thing about elliptic curve groups, which we already heard, is their group order isn't actually always the same. In this case here, if I compute modulo p, there's just one group that I have, and it has a fixed order. If I'm lucky, like in this case here, it's smooth, because 16 is 2 to the power of 4, which is a small prime. That's great. But I only have this one shot. Whereas if I could generate many elliptic curve groups by doing some computations modulo q, and all of them have a slightly different order, then it's more likely that one of these orders is actually smooth. So in other words, by doing this in elliptic curves instead of in the modular group, I simply have more shots of being successful, and thus a higher probability that I can do something efficiently. Now I still have a small problem, namely how to transport this algorithm or this idea to elliptic curves. So I need two things. I need some operation that I can compute iteratively, so the equivalent of a to the power of k. It's probably going to be k times something, some point. And the second thing I need is I need a way to detect when in the background, modulo p, I have hit the neutral element or something unexpected. Something that wouldn't happen modulo prime number. These two things I need. And actually, elliptic curves serve me them more or less on a silver plate, because if I write down how to do computations in elliptic curves, I get some nasty formulas like this one here. There is one interesting ingredient here that we care about, and that is this shape here. This appears whenever I double a point or add 2 points, where none of the two is the neutral point. In those cases, I always need to divide by some values. In other words, I need the inverse of the denominator here. And that's in each of these steps. Now I can compute inverses modulo prime number, but what happens when I try to do this modulo a number that is not a prime number? What problem will I run into? So when I try to do this division modulo a non-prime number n, if they do have a greatest common divisor of 1, everything's okay, I can happily keep computing. However, in case I try to invert an element that is not actually invertible, in other words, it has a common prime factor with n, then this inversion fails. It's similar to division by 0, a division by by an element by which I actually can't divide. So if I run into this problem, then while doing the division, using for example the extended Euclidean algorithm, I will get an error. I will get the information you can't actually divide by this. And the reason is this common factor. And this common factor turns out to be exactly what I'm looking for, namely a prime factor of n. So that's great. And it also already gives us the finished algorithm. So how does it work? I iteratively try to find a new curve and a base point on this curve. Finding base point is actually not that easy, but there is a simple trick that you can do, namely you can choose most of the curve description, then find a point, and then complete the curve description with this constant here, such that this point is actually on the curve. In any case, I generate random curves. I pick some large numbers with many small prime factors, just as in the other algorithm. And then I do my computation with this large number. In the previous case, we had a to the power of k. Now we take our point times k because we're in an additive group. And I keep happily computing until I run into one of these uncomputable operations, which resulted because I tried to do something modular number that was not prime, which means the corresponding elliptic curve thing isn't actually an elliptic curve group, because some of the computations just don't work. And I can detect this just like before with this greatest common divisor, now computed between our modulus n and this thing in the denominator that we had in the computations. So once I hit such a computation error, voila, I have found a factorization of n. Okay, so that's the follow-up to last week. Now let's briefly return to this week and let's have a look at the summary for today. So what we saw is that all the generic algorithms have this exponential runtime. Exponential in half the bit size, but still exponential. And in some cases, we do know how to make things better, how to do things more efficiently in sub-exponential time using index calculus, sieving methods, very similar to factoring. If this is applicable, then the hardness of the discrete log problem is essentially the same as that of factoring, meaning I need exactly the same key sizes. If this algorithm is not applicable, then I can use smaller security parameters, like in elliptic curves. So more specifically, when I can't do index calculus, let's choose a group order of 2 to the 2 times n, where n is the security parameter. If I have index calculus applicable, then I choose the group size by the same considerations as in the factoring lecture. And I have this point here in between, using this Poly-Kalman algorithm that we didn't cover. The main thing to defend against this was to make sure that the prime numbers produce subgroups which have a large prime factor. This is the reason why we had these safe primes earlier. I just want to recall that the safe primes are those p equals 2 times q plus 1, such that p minus 1 has one very large prime factor. Okay, so that's another thing to take into account. And with that, I'm finished with the content for today, and I'm happy to hear what questions you still have. While I'm waiting, I can tell you a few things about next week. Namely, next week you will have different lecturer. Marcus is going to have his first lecture. If I do remember correctly, it's going to be about quantum cryptanalysis. I might be wrong, but I think that's what it's about. And after this, we are also going to present the exercises that you have to solve for the KU part. And spoiler ahead, they are going to involve some factoring, but also some other things that we will only cover in the following lectures. I will be here for the next time in 2 weeks' time, unless there's a holiday in between, I'm not sure, but I think in 2 weeks' time. And then I think we're going to talk about lattices and using them for cryptanalysis purposes. Okay, I see a question here. What would be exam questions regarding discrete logarithm? Because this was quite mathematical. I hope it wasn't too deterring. I do have some exam questions here. So let's have a look at this. The first one is about talking about what the discrete logarithm problem is and whether it's difficult, so what parameters its difficulty depends on. Then here's a bit of a freestyle answering questions where you can pick your favorite discrete logarithm methods and explain 2 of them. Meaning you can pick, for example, the babystep giant step algorithm, which I think is easier to understand than the others. And what else do we have here? I have to quickly hide your question to be able to read it. It's about, it's about explaining the two algorithms we had a look at. And how it's related to factoring methods. So in all of these cases, I don't usually expect that you spit out all the specific formulas about how things worked, but that you convey the idea. So for example, in the index calculus algorithm, the idea was to first use equation solving to find the logarithms of the prime elements. And then in the second step, we can use a combination of these prime elements to find the logarithm of the challenge element. Or in the Pollard row algorithm, you can, I don't expect you to actually chew and spit out the entire update formula that these three cases that we had there, but say something like, you have a function that produces these combinations of y to the something, g to the something, and then talk about how memoryless algorithms can solve this efficiently. I hope this addressed your question somewhat. Let's see if there's anything else. And I can also reassure you, the first two lectures are by far the worst in terms of mathematics, because these are related to asymmetric cryptography. Whereas in the later lectures, starting in April, I guess, or after the Easter holidays at least, we're going to come back to symmetric cryptography, which I personally think is a lot less mathematical and more intuitive to understand. But it's still going to involve some mathematics. Okay, but less number theory, or no number theory at all. Okay, I guess that's it. Thanks a lot for the question and interactions. And next week, I guess I'm only going to join you in the audience maybe, but see you again in 2 weeks' time. Have a great evening.